over what. No worries. Welcome, everyone. I'm very happy to be here with you all and go over some graph data structure concepts with you. And I'm here to share that the knowledge that I've gathered over the years and kind of share my thoughts and ideas on graphs. So the agenda for today is to go over what a graph is and what are the terminologies associated with the graph data structure and how to represent graphs in code, common ways graphs are represented, and what are some use cases where graphs are used in the real world. And then we can go over some algorithms, commonly used algorithms associated with graph. And then we can see some code as well. And then if time permits, we'll go over some techniques and tips that will be useful for the interview preparation. With that said, I think we can get started. So what is a graph? It's a structured way to represent relationship between different entities. So you have many entities, and to represent the relationship that they have in between them, graph is being used. It's a recursive data structure. And if you see here, this is a graph that has a node, and all the nodes here are connected by edges. A graph typically is composed of nodes and edges, and all the nodes are connected by the edges. 12, 7, 4, 8 are the nodes, and they are connected through edges. The second one here is also a graph, but the only difference between this and here is the edges have some properties. So these are typically called weighted graphs, and they have some properties associated with each of the edges. And we'll get into the details of that in the later part of the session. Okay, let's go over some terminologies that are associated with graph. The basic unit of the graph is called a vertex, and this is also called as node. And every node is connected by an edge. So edge is basically the connection between the two nodes. So V1, V2, V3 are the vertex, or also called as nodes, and there is a connection between those two vertices. And vertices is nothing but just a plural form of the vertex. And two nodes, V1 and V2, are called neighbors if they are connected. So if they're connected directly by an edge, then they're called a neighbor. So here we have V1 is an neighbor to V2, and then V2 and V3 are neighbors. And it's also referred by a different term that's called adjacent nodes. So we can either call these as neighbors or adjacent nodes. Yeah. And what is a path? A path is nothing but the sequence of nodes that we can follow to go from one node to another node. So here, these two highlighted nodes, to go from this node to this node, we have to follow this route of going to this green node, and then orange, and then gray. So let's consider an example. Like if I'm at my home and I want to go to the parking lot, so I go from the place that I am to the main door, and then walk down to the stairs, and then get to the parking lot. So path is the way that I walk from one entity to other entity. So so in this case, it's from this node I go all the way right down, and then again back here. And path length is nothing but the number of edges that we have crossed during the path. So here there are, to reach from this node to this node, we have three edges connecting. So the path length of this is 3. Go from here to here, which is 1. There's one edge connecting here, and from here there's one more, and then that brings the total count of 3. So path length is nothing but like the number of edges that makes that path. All right. So a cycle in a node is called, if a path starts at the same node, at a node, and if it ends at the same node, then it's called a cycle. So, so here we start a path from this node, go all the way down back, and then this node again goes back to the node from which it originated from. In that case, it is called a cycle. A loop is nothing but if it has an edge pointing towards the same node. If the source and destination are just the same, it's called a loop. And here there is very few graphs allow these loops, and few of them they don't. So actually, many of them don't. All right, and then a connected graph means like if all the nodes are reachable from a single node. So this node here is not a connected graph because we'll not be able to reach to this node from this node. So this makes it a connected graph because we can go from every node to every other node in this graph. From here, I can go either here, 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 or from this node, I can go to any node in this graph. In that case, it's called a connected graph. A complete graph is nothing but if every node has an edge connecting to every other node in the graph. So here is a node and it has edges pointing towards all the nodes in the graph. It has edge pointing to this node, this, and this. So every single node in the graph does the same thing. It has nodes pointing to every other nodes in the graph. In that case, the graph is complete. Okay, let's go over some properties of graphs, commonly referred properties. The graph, the properties are based on the edge. So if the edge is in one direction, and yeah, so first let's talk about this directed graph. Here, the edge is just pointed in one direction, similar to what we have for like a linked list or tree. It goes all the way from A to B and B to C. There's no way that it goes back. In that case, it's called a directed graph. Whereas here in this undirected, it is two ways. The arcs and edges are pointed. It can go from 1 to 3 or 3 to 1. In that case, it's called an undirected graph. And a weighted graph is nothing but the cost or the cost associated with moving from one edge to the other, moving from one node to another node. So here, let's take an example of maps, and then to move from one place to another place, there's a cost associated with it. This could be anything, not the cost typically in dollars, but it could be anything like the distance. So that is represented within the edge. And we use that weighted graph in a lot of real-time scenarios, and we'll get to that as we go. But these are the common properties of graph. And if a graph is directed, it's called, if it has a directed edge, it's typically called as a directed graph. And if it doesn't have if it just have an undirected edge, then it's called an undirected graph. And yeah, now that we went through some graph properties, we can see like what are the real world scenarios where graph is being used today. So the friendship relationship on Facebook is a perfect example for graph data structure. Here, the vertices are the profiles and the persons themselves, and two persons are connected if there is an edge between them, and that's represented like they are friends. So you can imagine all the vertices are the profiles, and if there's an edge between them, then they are friends. And other examples, like air travel, where you can have the vertices as airports, and the flights that are connecting the vertices are referred as edges. And the third example would be simple maps, where you have the vertices are represented as cities or destinations, and then the edges are roads connecting those cities. So let's say like there is a city and there are like hundreds of roads connecting that city. So how do you represent that? Represent the graph in code? Okay. There are many ways graphs could be represented. Most commonly used ways are like adjacency list and adjacency matrix. So the topmost thing is you can just represent graph um, as like a set of vertices and a set of edges. For example, here we have a graph A, B, C, D, E, and then it is all connected. And to represent this graph, we either have A, B, we have all the nodes and under a set, and then we have all the edges in a set. So if let's take this E that has A, B, A, C, A, D. It represents every single connection or neighbor here in this structure. But the only advantage here is we wouldn't be able to like, in order to find a path or in order to find a node, if it's a neighbor of another node, we have to traverse the entire list, and that could take some time. It would be easier if we could keep track of the nodes and what are the edges that are emanating out of that particular node, and if we track them separately. For example, here you have the node, and you have the so the neighbors associated with node A are B, D, and C. So all those neighbors emerging out of A could be represented in a list or a set. So basically we have every single node and the neighbors of each of those nodes here. And in Python, it's easier to use like a dictionary where you can have the key as the nodes themselves, and the values are the neighbors associated with those nodes. And Java, we can use a map where the node to represent the node and the set of nodes that are the neighbors of those nodes. So this is better, but still better than the previous way of going through the entire list to find the edges, where you can, if you want to know what are the neighbors of C, I can just do a lookup of C and then find, but still I have to traverse and find like what are the nodes associated with C. Like if this looks easier when it has just two nodes, but if there are like hundreds of nodes, it still requires some traversal to go over every single node and find what are the neighbors to find if there is a particular neighbor that we are interested in is there or not. Another common way of representing graphs is called adjacency metrics. Here we use a two-dimensional metric to represent the relationship between the nodes in the graph. So it's represented by a n by n grid, and where each node is that are connected are referred here as like ones, and the ones that are not connected are zeros. For example, we have so many nodes A, B, C, D here, and I have listed them all under the column, and here all under the rows. And whenever there's a connection between a node to another node, that will be that here we are using a Boolean matrix where we're just adding like a one. If there's a connection, we just represent that as one, and if there is no connection, then we have that as zero here. Adjacency metrics is also used, but adjacency list is widely used. But adjacency metrics is slightly faster for lookup. For example, if you want to see that if there's a connection that exists between C and D, then it's just you have to it's a fairly easy lookup to find if there is a edge that exists between C and D. Whereas in case of list, you just have to traverse and see. But let's see like when to use an adjacency list and when to use an adjacency metric. So adjacency metrics is definitely good for lookup. So if you want to look that's easier, but it's going to take up a lot of space because you're going to represent every single element. And even though if they're connected or not, you still have like a presence for them. So it's going to end up taking memory. So let's say we have a graph that's densely connected. Like there are 100 nodes and all of them are connected, then it makes sense to use an adjacency matrix. But in scenarios where like there are similar 100 nodes, but only 2 or 3 nodes are connected, in that case, we can it's better to go with adjacency lists instead of metrics. So it's the trade-off is space versus time. Let's look at how this really looks in code. So here is an implementation. This is written in Python. It has like a constructor that has that represents the properties of the node. So the node has a value, and that's set here. And it could also have other properties like the color, and that is also represented here. And every node has a list of neighbors that that it is connected to. And in order to represent that, we have neighbors as a set. And so here is what the constructor we have for this particular node. Now we are creating nodes. Just a second, let's see. So here we are trying to create nodes using that. Trying to see if I can draw. Stay with me for 1 minute. So we have added 3 nodes A, B, and C. And I'm trying to see if I can draw those neighbors as we add them. Okay, cool. Okay, so here this line has, so here we have created a node A, and so there we have a node A, and then created a node B, creates a node B with a value as B, and then there's one more C. So now I'm adding A's neighbor as B, and B's neighbor is added as A as well, because this is not a directed graph, this is an undirected graph. So A is B's neighbor and B is A's neighbor. And then we have another neighbor for B, that is C. So this is how this graph looks like. We are first creating the graph and then adding the neighbors. And to add the neighbors, we have a set. This is just a more formal drawing. Okay. Let's look at some common algorithms associated with graph. The most commonly used algorithm is depth first and breadth first. These are traversal algorithms, but there are also other algorithms like topological sort, coloring, and Dijkstra's shortest path. But in this presentation, we'll just focus on the depth first and breadth first and try to get comfortable with that. Cool. Oh. Okay. First, let's look at the breadth first, or maybe the depth first. Okay. So depth first and breadth first are both traversal algorithms, but the order in which we traverse matters, and that causes the difference. Both depth first and breadth first helps us to visit every single node, but the order is going to be different. And we start with one node and then follow all the paths and try to visit other nodes in that graph. And we keep doing that until we find the target node or we reach the dead end. While doing this kind of traversal in graph, there is a possibility of cycles. Like we keep visiting the node that we already visited. So it's important to track the nodes that we have already visited to avoid the infinite loop with the traversals. So we always have to track like the visited nodes in a set or a list, and that helps to avoid going in loops. So first, the depth first involves visiting all the nodes, choosing a path and visiting all the nodes in that path, and keep doing that, and then visit the next path. Once that path is completely visited, then we explore the next path. This involves scanning of all the edges and nodes. So the time complexity is O of V plus E, where V is the number of nodes and E is the number of edges. The space complexity is O of V. And this is usually implemented using recursion. We'll see how that happens, but we choose a path, recursively go searching on that path, keep going until we find find a end. So, and if we use, when we're using recursion, it's important to know what our base case is. We'll see that here. So this is like the pseudocode where you pick a starting node and go to all reachable nodes from that node and keep going outward, keep going until you find an end. And once you find an end, then you backtrack and go to the node from where you came from, and then explore that path. So here, I have a single node in the graph, which I'm starting with arbitrarily. It could be any node, and then process that node. And once you process it, you mark that as visited, so you don't visit that again and again. And you add that node to the visited list. And then for every neighbor of that particular node, you perform a DFS. Like you go deep and see if that node is already visited or not. And you do that only for not visited nodes, nodes that are not visited. Go here. So this is the code for depth first search. Here is a graph, and here the graph has, it starts with, there's no starting node here. So for reference, I have it as 5 here. You have 3 and 7 are the neighbors of 5, and that is represented here. Every node and the neighbors associated with those nodes. So 5 has neighbors 3 and 7, and that's been represented here. And 3 has 2 and 4, 7 has 8, and 2 has nothing, and 4 has 8. 4 has just 8, and 8 has nothing. So here is a graph, and then as I said earlier, to keep track of the nodes that are visited in the graph, we have a set, and have a set called visited. And here's the DFS function that takes the visited, that takes the set, the entire graph, and the node that we are starting with. And if that node is not in visited, then you process that node and add that node to the visited list. And then for every neighbor of that node, let's say we start with 5, then for every neighbor of that node, we perform a DFS. So here we picked 5, and then 5 have 2 neighbors, 3 and 7. So we have to explore for every single neighbor of that the node. So let's start with 3, and after going to 3, we have to explore what are the nodes that are connected to 3, and here we have 2. So we just keep going deep. Let's do a sample traversal and see how that works. Okay, so here is a graph, and it's all connected. It's a we start with arbitrarily. I'm picking a node to start. We'll choose A, and so I'm picking a neighbor here. I'm choosing B to start with, and go from B. I should go everywhere we can get to from B. So from B, I can get to C. So I go to C, and then after we reach C, we have to see, like, are there any nodes here, are there any nodes that are emanating from C? No. So we have reached the dead, no, the base case, we could say. So the base case for this could be either we reach a node that is already being visited, or there are no nodes outgoing from that particular node. So from C, there are no nodes going. So I'm done with this path. So I go back. We go back to the node that we came from. So go to B and see. Okay, I have completed everything that I had with C. Are there any other nodes that are associated with B that I can explore? There are no nodes here. So again, I go back to the A node and see. Okay, I've explored all the paths that are emanating from B, and I wanted to explore the other path. I've completed one path completely, and then I go to the next path. So the B arm is finished, and then we get to the D arm, and here I go to D and then see if there are any nodes that are connected to D. Yes, there is. So I go and visit E, and again, after are there any nodes that are being that are connected to E? Yes, there is E. There is F, and there are two nodes actually connected to E, F and G. So I go first. I choose F to go to F, and then again I have to see like if there are any nodes that are emanating from F that I have to visit. Apparently we had hit the base case here. There are no nodes that are happening at F. So I go back to the node that I came from. Here it is E, and are there any other nodes associated with E as F is already completed? Visiting F is already completed. So yes, there is one node G. So go and visit that node G. And are there any other nodes that are associated with G that I have to visit? No, there are no other nodes. Okay, we have hit the base case, and then now you go back to the node that you came from, E. I've finished everything that are associated with E, G, and F. Are there any more nodes to visit? No, there is no node. Go back to D. Any other nodes to visit other than E? No, there is no node. If there is one, it will visit that. Here in this case, there is no node, and then go back to A. I have finished A. I've completed B arm and D arm, and there is what are the nodes left associated with A, or the neighbors associated with A was only H. Go and visit that H. So this is like a simple DFS traversal where you pick a neighbor, you choose a node, pick a neighbor, go deep, keep going deep until you find the end. And then once you found the end, then backtrack, go back and see if there are any other nodes associated, and then just keep doing for all the nodes in the graph. The next thing is the next traversal that we discussed about earlier, like the BFS, and why would one use BFS? Let's see that. Okay, here in my graph, I was able to find if there is a path that exists between two nodes, but in order to find the shortest path, how do I find the shortest path? So that's when breadth first comes into picture. So breadth first involves processing a node and processing the neighbor of a single node, and then processing the other neighbor. So first it involves processing all the neighbors of that particular node before it moves to the next level. But while processing that particular neighbor, it also maintains a list of nodes that it has to process, list of neighbors connected to that particular node you're visiting. And it maintains like a to-do list of neighbors that it has to visit. And in order to maintain that list, you use like a queue data structure. We'll get and we'll see in detail of how that works. But it's important to understand, like for breadth first, we first visit all the neighbors that of the node that we are visiting. And while visiting the node, we are also going to keep track of the next generation of nodes that we are going to process, that we are supposed to process. And in order to keep track of the next set of to-do list of nodes, there are different, we use queues to do that. There are different data structures, but then queue fits perfectly for this use, where I want to visit a node and I want to visit few other nodes are associated to that node at a later point. So after you enqueue, first we'll add a node to the queue, and then dequeue from the queue. Dequeue happens from the front of the queue, and then enqueue all the neighbors of that as a to-do list to the back of the queue. Let's see how it's being done. So initially, I choose a starting node and visit all immediate neighbors that are connected to that starting node. And while visiting, I'm also gathering information about the next level. So assembling what is needed for the next level of processing. So keep doing that for every single node. So first I complete the immediate nodes, and then branch out that are to nodes that are 2 hops away, then 3 hops away, and just keep doing that to the end till the end of the graph. So to keep track of the nodes to visit, we use a queue. And initially, the node just stored the node v1 and mark v1 as visited. And while there is elements to process in the queue, I have to dequeue a node from it, node from the queue, and mark that node as visited. And while visiting the node, I also have to assemble all the unvisited neighbors of that particular node. So I see the neighbors of that node and I add it back to the queue. So here is the code for breadth first search. This is the same representation of the graph that we had in our previous slides, and you have like a visited list to keep track of the nodes that you have already been visited. So don't end into a loop of visiting the same node again and again. And then queue to maintain a list of to-do list of nodes that needs to be processed, and then get into the function here that takes the visited list and queue and the graph and the node itself. So here in the visited, I'm adding that node to the visited list, and then also adding that to a queue initially. This is the generation 0, like the first node here. In this case, it's 5, and pop out that element from that queue, process that element, and for every neighbor for that node, in this case for 5, we have 3 and 7. So for every neighbor, if it is not visited, then we add it to the visited set or list to make sure that to acknowledge that we have visited that particular node, and then add it to the queue. So when I add it to the queue, it adds at the end, like you are adding to the back of the queue. We'll see in detail how that works here. So here is a breadth first traversal of this graph, and start with a node, starting with A here, and A has 3 neighbors, B, D, and H. First, visiting the first neighbor of A, which is B, and I have looking here if there are any other nodes that could be that are going out from B. Yes, there is a node C, but I'm not ready to process that node immediately. You just add that as a to-do list, and I will process it when you're getting to the next level. So the intent here is to process all the neighbors that are immediate neighbors with associated with the node that we are visiting here. So A's immediate neighbor is B, but while visiting, also keeping track of what are the nodes that needs to be visited in the second generation, assembling or collecting the nodes that needs to be visited for the second, for the next time. So from A you have B, and B B's neighbor is C, that is added to the queue, but it's not yet processed. And then once it's finished, there is no more nodes, and you go back to A. Now C is already in the queue because B has added it, and there's going to be 2 iterations, but since we are using that visited, this C will be just visited once because we are already keeping track of the nodes that we have been visited. So when it is B, for B, the nodes emanating out of B is C, and we have added it to the queue, and then process the next neighbors, keep processing the immediate neighbors of A, which is D in this case. And after we visit D, are there any nodes that are associated with D for the next level? Yes, there is a node E. So add E to the queue, but still not process it. Just keep adding it. You're collecting the information for the next level here. And once that is done, then go and visit the other neighbor of A, which is, in this case, it's H. So here in this, we have processed the first level 1, from the node that we started. B, C, D, H are in one level. So we once that is completed, only then you go to the next level and go to the level 2 here to see what are the nodes that are available. So the queue would have had C at that point. C doesn't have anything, so it's already visited, and then the queue would have E added because E is something that we added when we visited D. So E would be the element out of the queue. When we pop the element out of the queue, it will be E. And then look at elements that are connected to E. So there is one, so visit E. And while at the same time when I'm visiting, also keeping track of what are the neighbors associated with E that I need to have, that I need to process. Here it is F in this case. So add F to the queue. So and then there is G, and add G. Are there any nodes associated with G that I have to process in the next set of generation of nodes? There are no nodes, so it's done. So go back to the queue and pop out, and now E will be the only F will be the only node that will be popped out of the queue. And after we visit, are there any further nodes connected to F that I have to visit when I have to visit it later? No, there are no nodes, so it just gets printed here. As we visit the nodes, we kept printing the nodes, and that's how we have got to this. And this is like the traversal of this particular graph. Any questions so far on these, specifically on these 2 traversals? Because these are important. These are most important traversals when you wanted to solve graph problems, and it's very important to start to learn them and understand them. So if I'm happy to discuss if you have any further questions before moving to the next topic. Feel free to unmute yourself and ask for questions if you have. If you want me to go over the traversal again for DFS or BFS, please feel free to do that. Spell that. And
yeah, I have a question. So is it always taking the node from the left side first?
Not necessarily. So the compiler can take anything, but here it just picks a neighbor randomly. Not necessarily it has to be B. But here for explaining, I just picked B, but it could be D as well. It could be H. H could be picked first. But all it cares is picking the neighbors of the node associated with, here it is A in our case. So yeah.
All right, thank you.
Welcome.
Hi, I have a question. If the node A to C gets picked first by the compiler, then when it reaches the node A to B, at that point, it will not visit C because we have already visited. I mean, but how is it keeping track of it?
So first, let's say it picked C here, and C is added to the queue initially, and you pop out of the queue and see if C is visited or not. But I mean, C is already visited. There are no outgoing edges from C, so it will go back. So C is already in the visited list, right? So it gets added to the queue, and it gets added to the visited list. And then you go to after it finished this arm, it will explore for other neighbors, and this time it has encountered B. So when it goes to B, it will look for if there are any other neighbors that are available, that are associated with B. Yes, there is one node C, but it will, but before adding to the node, we have a check that if is that already visited. So C is already visited. We have that in a list of nodes that are already visited, so we don't do it again. And then it understands that C is finished, B is finished, there are no more nodes, and then it goes to the next node, H.
Thank you.
Welcome. Any more questions? Okay,
there's one question in the chat, which is, how do we decide the starting node?
We wouldn't be able to decide that. All we can do is have a for loop to visit all the neighbors of that particular node, have a for loop. Let's say we have started with A, we wouldn't know that it has to pick, we couldn't tell that just start with node B. It could be any node here. There could be any number of nodes that are emanating from A. There could be hundreds and thousands of nodes, and we don't know which node to go. So it just picks a node in real world scenarios.
One question here. So, in a typical tree kind of data structure, right? When we have some problems related to that, we are given the root node, right? So here, what do we expect? We'll just be given a node, or how is it like?
It could be anything. Thanks for asking that question, because I had that in the future slides, in the next slides, of how this graph is different from tree or a linked list, where you have a start, you have a starting node or a root. But here in the case of graph, all you have is a graph. And sometimes you could be given with a start node, like start from node A in the problems. But generally, you just have the graph itself, and all you do is use a for loop to go over the neighbors of the nodes that you choose. Yeah. Sure.
Sorry, I have one more question. So let's say if you start from the node D, that means not all the nodes will be covered, right? It's just, you just cover the nodes that is sort of below it, right? So that means if you start from D, A won't be covered.
In this case, it's a directed graph. So in this case, no, it will not be covered. But in case if, let's say this is not a directed graph like this, it's an undirected graph, you just don't have these arrows. In that case, A will be covered. But but you're right. In this scenario, this is a directed graph, and when you choose D, all you have is E, and just E and then F and G. So that's why it's important to use like a for loop to go over every single node of the to iterate over every single node of the graph. We'll see that in like in the following slides as well, a little bit. Okay, let's move to the next slide here. Okay, so let's say there's a graph that is from A to B and C, D, E, F, 6, H. Now, my intent is to find if there is a H node that's connected to A. And if you do a BFS, then just have to find, so it arbitrarily picks a neighbor, and in this case, let's say if it picks B, and keep searching, keep going until it finds H. So it found H here, whereas so it explores in depth, so it found the node H here, whereas if it's a breadth first, it will visit all the neighbors in the node. So in case of breadth first, it will visit B, and it will see like if there are any neighbors associated with B. Yes, it has C, and it will just add it to the to-do list, but it is not yet processing it. And then it will go back and see if there are any other nodes that are associated with A. Yes, there is H, and it will visit that node. We found the destination. It will return. It doesn't have to necessarily process all the list of nodes that it had in the to-do list. So in that way, breadth first is better. It's easier when you want to find the shortest path. So here in the same problem, if I had to find this particular node H, if there was a depth first search done, I would have still found H, but it is after taking 7 hops from A to B and B to C, D, E, F, G, H, and everything. But whereas in BFS, it would have just been in the first shot itself, or in the second shot, like where you processed all the nodes from B, and you didn't, you process the neighbor of A, which is B, and you have other nodes, but you just added it to the queue. We haven't processed it yet. Go back to the A to see if there are any other neighbors associated with A. So finish level 1 first here. So this is level 1, and just in that way, you would have found it. It would have found this particular node H. Let's say this graph is like connected. It has multiple levels, but then breadth first is helpful to find like the shortest path or the easiest path. That's something I just wanted to highlight here. And let's look at the weighted edges. I have mentioned as A, B, C here, but you can just think of this as cities like San Francisco, and like just think of SFO and MN. Just think of this as a map. So to get from one path to another path, there is a cost associated with it. It could be like the distance or the actual cost in dollars. That is being represented here in the edge. If I'm interested in just looking at what is the easiest way or what is the quickest way to go from this place to one place, then it's definitely A to B. Whereas if I'm interested in just going and exploring all the all the different ways before I go to M, and that's and let's say it just costs $100, but so to go from SF to MN, you just have one direct flight and just pay 500, or take this path that takes 100. So all those representations are being done using a weighted graph that tells us what is the cost to move from one particular node to another particular node. And even in our GPS maps, like you have different routes, and based on how easy it is, like the shortest path to reach from one destination to other, kind of random, you kind of pick that path to go to that place. So so behind the scenes, these type of traversal algorithms and these weighted graphs are being used. And Let's quickly look at one of the common algorithm that's being used. It's called topological sorting, and it's nothing but just ordering the vertices such that, like, if you have a path between two nodes, let's say U and V, and if you have a path from U to V, then it means that U has to be completed before V. So U has to be done first before V. Let's take a common example of the washing clothes. So here there's a representation from 1 to 2, and 1 represents washing and 2 represents drying. So you have to finish washing before you have to dry your clothes. So it just happens in a sequence, and this is typically used for scheduling problems, like where one task is actually dependent on another task. And this is these type of problems, like where how many semesters you need to take, how many semesters it would take to finish all the courses in a particular curriculum. So for all those type of problems, we use this topological sorting. It's applicable only for directed and acyclic graph. Acyclic graph is nothing but a graph that has no cycles. So let's say there is a cycle, and we won't be able to do this topological sorting if there is a cycle. So this is applicable only for directed and acyclic graph. First step is to arrange the graph in a specific order based on the incoming edges. Like this graph, so this is based on one on an order where the edges are just pointing in one direction. So that's the first step to do a topological sorting, and then do a DFS and save that information that save the nodes that you have visited. But this is just to give an overall idea of what topological sorting is. And here are some common problems. Before that, I'll just get into common tips is implementing like a basic traversal like DFS, and DFS is very important, and knowing to code them quickly, like as early as possible. Like just have that understanding of DFS and BFS, and able to code that will help you solve other graph problems as well. And here it's important to, as I said earlier, we discussed earlier, like it's all the graphs would not be connected. Let's say here there's a graph, and here there could be another graph here, and but it could still be a same graph, but the nodes are all not connected, or one node could be connected. So so in this case, it's better if you take all the nodes like A, C, D, E, D into factor, instead of as we said earlier, linked list, we'll be given a single node, and you can just go all the way down just following that node. And similarly, in trees, you have a root, and you just go all the way down following that root. But here, it's different. So you give an entire node, entire graph. Sometimes you could be given just a node that you have to process, but most of the times it's the graph being given. So that's one thing. And to know if that graph has a cycle or not, it could be done like by just keeping track of the number of times we visit a node. If we visit the same node twice, then it means that there is a cycle. Like there is a path that starts from the same node and ends at the same node. So and just keep doing the DFS here, so you kind of know if we have visited the node more than one time, and then you'll know that there's a cycle. And to see if there is a path, of course, you can use DFS or BFS here. But to find if there's a shortest path, then I think, as we discussed earlier, BFS makes more sense than DFS. And here are few of the other examples for BFS and DFS. You can just take a screenshot of it if you want, but practicing these problems helps you solve any problem associated with graph. But I would say you can start from like basic traversals and then go for like advanced, before going for advanced algorithms like topological, so I mean like Dijkstra's and other advanced algorithm techniques. So if you get comfortable with these, I think that's a good step to go in solving graph problems. Yeah, I think that's pretty much I had. And if you have any questions, we can try to answer them and get into a discussion if you want, but I'll leave it up to you guys.
Thank you so much, Maha. That was so great. I'll give everyone a few minutes to like process and think if they have any questions. Oh, someone posted in chat. An undirected graph is connected always. Or is an undirected graph always connected?
Not necessarily always. An undirected graph. So here is an undirected graph, but they're not connected. Connected means you can reach from one node to every other nodes. So from A, I can reach to B, D, C, but from C, I cannot reach to A, or from A, I cannot reach to C. So it doesn't matter if it's a directed or undirected graph. So here, it's still not a connected graph. I hope that answered your question.
Someone else asked, have you been using graphs in your job?
I've used, not a lot, but I've used in the past, but not a lot. But yeah, I think these, it's just that I didn't get a chance to work much.
Yeah, there's some really interesting applications of graphs. Like if you think about like computer networking and like CDN, content delivery networks, it's all just under the hood like graphs.
Yeah.
So there's a follow-up on the undirected question, like from C, you can reach back to A.
Yes, but yeah, from C I can, here it's undirected. So from C I can reach A. Yeah, I think that's right. From C I can get to A, but I don't have like a direct connection between A and C, which is still fine because I don't need to have like a direct connection. I can still go from A to C and from C to A. Yeah, but but would I call this as a connected graph? No, because I have to visit. I cannot like it's still not connected. Like A and C are not fully connected. So I would be hesitant to call this as a connected graph.
And someone asked, are linked lists and trees considered types of graphs or completely separate types of data structures?
No, trees and graphs are like recursive data structures, but they are different type of structures, and they have their own use cases. And one other difference between linked list is in linked list you still have like edges connecting from one point to another, but there is no, you don't have any weight or anything associated with the link. It's just a pointer to reference to the other node. Whereas in graph, like even the edge, it could have some properties. It could tell like how what is the cost associated for the going from one node to another node and so on.
Okay, I'm gonna stop recording.